Hi, I'm David Baker of Origin Live. This is my dad and our company founder, Mark Baker. So we had a question in recently, which is exactly on one of the things we've just been discussing. So can you please cover the topic of dynamic and static arms in detail? Start off, what is a dynamic arm? What is a static arm?
Okay, excellent question. I don't know what percentage of the market actually uses dynamic or static. I would suspect it's almost 50-50, but probably many more on the static side. So if you can imagine the tone arm, all right, we've got a fulcrum here, that's your pivot, all right, and it's free to move up and down in the vertical plane on your record. This is your cartridge and stylus. A static arm relies on the downforce here being created by the weight of the arm, and you've got a counterweight on this side here.
So this is our tracking force.
So you've got and that gives you, say, a nominal 2 gram tracking force, okay?
Okay. Now,
if you've got a dynamic arm, which is Rega and Linn, for instance, if you've got a Linn ITOC, you've got this dial for the tracking force on the yoke. So you set it at 0, and then you get the arm, obviously with the cartridge all aligned and in place, you get the arm perfectly balanced using the counterweight here, and then a spring, which is carefully calibrated, okay, so it goes round and round, is on a dial here, and you then dial in the tracking force you want. So that the arm...
you're tensioning the spring.
Yeah, so it is then, the spring is applying the downforce.
Right.
And the reason they call that dynamic is because it's constantly forcing the arm to go down. Whereas if you're relying purely on a weight, then you've got inertia coming in. So when the arm hits a supersized warp, and it would have to be a very big one, the arm goes, ooh, and then has to slowly come down again. Except in reality, these warps so few and far between, you just ignore them.
And record flattening exist, and all kinds of tactics exist to flatten records.
Yeah.
Yeah.
And all I can say is that, in theory, the dynamic force is the way to go. In practice, well, yeah, because it gets over your inertia problems. You've still got inertia, mind you. You still have the inertia, but you've got an additional, because you've got a dynamic loading as well, the impact of the inertia, the percentage impact of the inertia is less. So in theory, it's the way to go.
Can I ask another question?
Yeah.
Is there also a resistance to movement there where it's constantly applied? I know that static is also constantly applied, but what I mean is there resistance to movement for it to tackle groove, vertical tracking error, warps, that kind of stuff?
Well, that's a really good question. How much resistance the spring has depends probably on the length of the spring, which is why it has to be quite a long spring, I think, so that it gives a linear force and maybe doesn't give you that resistance that you're talking about.
Okay, so that's not such an issue. So we've done the theory. In practice,
the vibration created by the spring or whatever device you're going to use probably to do this is quite high. And it's the same argument as with the falling weight mechanism. Okay, so just to finish this, I would suggest very strongly that it's not a good idea to try to put dynamic loading on this, for the simple reason that whatever mechanism you use, it's going to couple with the outside environment and put vibration into the arm, which is what you want to really avoid.
By outside environment, what do you mean there?
Okay, very good question. Basically, whatever device you use here will have to be attached to the base, a fixed point basically, which is the base of the arm or something, or a strut or whatever. And that is going to feed vibration into the arm one way or another.
Right.
And it will interact. It'll create a resonant loop. Vibration is very difficult to predict sometimes, but it will interfere with it.
Mm-hmm.
I mean, if you think about it, if a side bias ball, which is only going to be exerting 1/10 of a tracking force, you're effectively, even if you had something as low friction as a side bias ball applied to create tracking force, which you could do, you could create, it's 10 times the amount. You've got to create 2 grams of tracking force as opposed to 0.2, which is of the side bias force. And that is 10 times the amount of difference that you'd hear when you remove our side bias balls. So it's just a balancing act between what's worse, the slight loss you get from an inertial bump here, or the coupling that you get when you try and get side force using a spring. Because I won't go into spring mechanisms and that, but they all effectively end up attached to the outside world here.
Mm-hmm. There we go. Thanks for watching. Please like, comment and subscribe, and ring the bell notification if you can. And in the meantime, happy listening.